Good. Let's imagine you are tasked to design an architecture for a cloud-native product at your company. And let's imagine you have gathered all the necessary requirements such as performance, scalability, reliability, and cost. And at that stage, you might ask yourself, what would be the optimal compute platform to choose? Should you run your application with containers and an orchestrator, such as EKS or ECS, or can your applications be run by serverless functions? So today we want to help you navigate the path and help you to choose the right tools along the way. We want you to get a better understanding of the trade-offs, and therefore let me all welcome you to SVS209, Containers or Serverless Functions, a path for cloud-native success. My name is Maximilian Schellhorn. I'm a Senior Solutions Architect with AWS, and I'm joined by Emily Shea, Worldwide Lead Serverless. So at the beginning of our path, we will get an overview of the fundamentals that makes each technology unique, and then we will evaluate them from an operations, integrations, portability, and pricing perspective. And last but not least, we will dive into real-world customer scenarios to apply the things that we have learned along the way. So let's start with our first candidate, containers. And we have seen a big trend in evolution in the container space over the recent years, because in contrast to traditional virtual machines, containers share the kernel of the host operating system, and therefore they tend to be much more resource efficient. Right? In simple words, I can put many more containers on a box than traditional virtual machines, and therefore I have a better resource utilization, and they also tend to start up faster. Now, when we look into the anatomy of a container, we see a couple of components involved. So first, the container is defined by the container image, and it has a couple of layers in it. So we have the base image, we have the runtime, such as Java or JavaScript, for example, and we expose a certain functionality, like an HTTP web server on a given port. And to do that, we sometimes leverage frameworks, but the most important part is our application code. Now, the container itself needs to run somewhere, and this happens on a compute node. And on that compute node, I have my container runtime, which is the piece of software that makes the container portable. So if you have a container runtime and I have a container runtime, in an ideal world, we can exchange that container because it brings all of its dependencies with it. Now, running a single container is relatively easy. I just do Docker run locally, right? And I am done. However, in a production environment, it's a bit more advanced, right? I want to run multiple instances of that container for high availability, or I want to run different containers. So therefore, I'm relying on a container orchestration tool that helps me with that. So whenever a container is unhealthy, the container orchestrator will ensure to spin up a new container instance. Now, the container orchestrator relies on certain things such as load balancing, for example, and also giving the pods, for example, IP addresses. So I need some form of networking that is usually involved in those scenarios. From a lifecycle perspective, I think that's pretty common, as also in how we have seen it with virtual machines, right? So I have an initialization phase. So in that case, I pull the container image, I start it up, and then I have my running application. And that's usually longer running. So I expose a certain functionality. I might have a background job that is running, or I might have a listener that is constantly pulling from a queue. Now, there are multiple ways to get all those things into production. And I will start off with probably the most familiar one, which I call server-based containers. Now, with server-based containers, we see we have already quite a few components set up. So we have networking, we have the VPC, we have a load balancer, we have a NAT gateway to talk to the public internet. And we have, most importantly, our compute capacity. So Amazon EC2, where the containers will be eventually deployed. And now to kick things off, I write a task or a pod definition with my container image that I want to choose, CPU, memory, maybe some environment variables. And then a container orchestrator will take care of deploying the actual container in form of a task or a pod on that compute node. Now, the implementation of this orchestrator, they change, but the concept will always be the same, right? They take that definition and they put it on existing compute capacity. When the load increases, so when my container reaches a certain threshold, we will add more containers on that given machine up until the container, or actually the compute node, is fully utilized. And then we are relying on tools such as cluster autoscaling or Carpenter to give us additional compute capacity to be able to accommodate the additional containers. And Carpenter does a very great job in doing that. So based on your configuration and availability and pricing, it searches for optimized compute instances to be able to place your containers on that. An important thing to mention here is that scaling is based on utilization, right? So usually I define a threshold, as I said, based on CPU or memory utilization of a container or even of the machine, to then scale up additional workloads or additional nodes or containers. And then usually we're not making that 100% utilized, right? We want to still have some room in case we get a sudden load spike that we're still able to redact and create additional capacity. Now in this environment where we have full control of the entire stack, networking, our compute nodes, right, and scaling, we also tend to not only scale our workloads, but also our teams and maintenance processes, for example. We might not only want to run applications, but actually infrastructure components. We want to maybe run databases or additional things like message brokers. And this is where the whole trend of platform engineering came from. Because we have that full control, we can build great abstractions on top of that and provide that to our teams. So if we summarize that, what we have just learned is with server-based containers, we have a familiar environment and a broad choice of open source projects that we can choose from. We have full control and debugging capabilities of the entire stack that you see here. And we have the flexibility of the infrastructure. We can decide what should run or which instance types there should be. However, we also are responsible for cluster operations, right? We need to think about upgrades and maintenance, right? CVE patching and things like that. There are already ways to reduce that responsibility. So you might be familiar with managed node groups, or you have seen the announcement around EKS Auto Mode. So there are already tools to reduce that responsibility, but maybe we can even go one step further. So can we reduce the operational effort in that case even further? And this leads us to serverless. So can serverless help here? And I want to spend a brief moment here on the terminology, because we see people often get that wrong. We see great headlines with containers versus serverless, for example. Right? But what does serverless really mean, right? So at the core, it's a way to build and run applications and services without having to manage infrastructure. So what does it mean? So first of all, and we probably all know that, in serverless there are still servers under the hood. Right? So this is Delin from our infrastructure delivery team, so you don't need to deal with the servers, but Delin still has quite some work to do. But beyond that, serverless can mean many things to different people. For some it's scale to zero, for others it's maintenance or no maintenance or upgrades or rapid scaling. Right? But the most important aspect is what serverless is not. So serverless is not a synonym for specific technology. So serverless does not equal to AWS Lambda, for example, or function as a service in general. Serverless is more than functions. Think about S3, API Gateway, SQS, for example. And now coming back to our example, we can also run our containers in a more serverless fashion with AWS Fargate. So Fargate is a serverless compute engine that lets you run your containers on highly available and up-to-date infrastructure. Right? So if we look at our example, we still can leverage our networking stack and also our container orchestrator, but now the containers are placed on newly provisioned Fargate hosts that use up-to-date runtime, and they run on a single-use and single-tenant compute instance, and they are isolated by a virtualization boundary. It also helps us to automatically scale our workloads. So we don't need to rely on things such as cluster autoscaler anymore, because we don't need to provide additional instances, right? This is something that Fargate handles for us. So if we compare that we see here the different layers of abstractions, right? Here on the left side, we have all the full control, and with Fargate, we can already reduce some of that responsibility. And we can take that even one step further if we think about App Runner, where we don't even need to think about the networking stack or load balancing, but we can expose an HTTP server directly. Now you might ask yourself, okay, we have server-based containers, we have serverless containers, so now we have everything, right? So why can't we just build anything from containers, right? Are containers maybe the answer to anything, right? To everything, and compute infrastructure, right? And I would argue that there are still two potential areas that we can optimize here. And the first one is, from a scaling perspective, we are still dealing with larger buckets. We're dealing with machines and containers, and they are based, as we said, on utilization, 60%, 70%, 80%, right? And we want to keep like a certain threshold ready to be able to scale. So we're never 100% utilized. So maybe we can improve that. And the second thing is the long-running nature. We have machines, we have containers, we have load balancers. And while you could automate the shutdown of a given task, for example, you still want to expose that for a longer period of time, or at least your container orchestrator keeps running for a longer period of time. So maybe we can also do something about that. So in those two scenarios, we will see if maybe serverless functions can help. Emily.
Thank you. All right. So I will pick up where Max left off, and I will jump into the second half of our equation today, which is talking a bit about serverless functions, in particular the AWS Lambda service, and what makes that unique, and what are some of the specific characteristics that it has that are a bit different from containers, as we've just been learning about. So to start off, let me take you through the basic anatomy of a Lambda function. So when you sit down to write a Lambda function and think about the code in there, there's going to be about three main components that you'll be thinking about. So the first off is you have your function handler. So this is the piece of code that is running every time your function is invoked. You can write this in your favorite programming language, and the function handler takes an input argument as well as an optional context that you can pass to it. So in our example, we have a very simple Lambda function. All it's doing is it is taking that unique request ID out of the context, and it's just logging that. Now, our function code needs to run somewhere. In the case of containers, we talked a bit about compute nodes and those running on compute nodes. And for functions, you have a Firecracker micro VM. This is managed by Lambda, and it's running on bare metal EC2. There's no kind of servers or underlying infrastructure that you're needing to manage. All of that is covered by the Lambda service. And that Firecracker micro VM is what provides the isolation between each of the function executions. And so the really important thing to understand around Lambda functions is that, and that might be different from how you've built in the past if you're new to functions, is the fact that you are not directly calling your function code. So you are not creating an HTTP listener or opening up a port on the micro VM. Instead, the Lambda service is sitting in the middle, and the Lambda service is the one that's invoking that function code. Now, the Lambda service, you can make requests to it via the API, an API to make requests to endpoints, or the Lambda invoke API, or different services, which we'll talk about on the next slide. And the Lambda service, you invoke that, it takes the inputs and passes that to the function code, and then returns whatever results are passed back after the function code is run. Now, the Lambda service does a number of cool things. First of all, obviously, it manages all of that infrastructure, so there's no servers or clusters that you're needing to think about, needing to patch, needing to operate and maintain. All of that is handled by Lambda. The other thing that it does that's particularly cool is it handles all of the scaling. So the number of functions that number of function capacity that you would need to handle the requests that are coming in, Lambda takes care of all of that for you. And this becomes particularly powerful when you think about event-driven architectures and writing Lambda functions that respond to events and messages that might be coming in from other services. So let's take a deeper look at that one. So here's an example of a very common event integration that you might be building with Lambda. So reading from an SQS queue and processing the messages. Now, if you were building this on a container or writing code to run on a VM, you might need to write a poller, something that's always running and always pulling that queue to see if there's new messages coming in. Whereas in the context of Lambda, you're able to make use of Lambda's event source mappings. So these are particularly cool. They are direct integrations with some of these upstream services like SQS. And what they allow you to do is Lambda is actually doing the polling and doing the reading from that queue. It takes the message that is sitting in the queue, and then it invokes the Lambda function code with that message specifically. So that really reduces the amount of code that you're needing to write yourself that would need to process and extract those messages and pass those on. The other particularly cool thing that the event source mapping will do for you is that it also is aware of things like queue depth, and it's able to scale up additional capacity as needed based on the amount of messages that are sitting there waiting in the queue to be read. Now, these event source mappings are available for services like SQS. They're available for Amazon MQ, for RabbitMQ and ActiveMQ, also things like DynamoDB, Streams, Kinesis, and Kafka. And actually, in the last 2 weeks, we released a new feature called provision mode for Kafka event source mappings. So if you're running self-managed or MSK for Kafka, then and your application has very stringent performance requirements, you're now able to use a provision mode to ensure that you have the amount of capacity in those event pullers that you would need in Lambda. So some particularly cool things that you can do with that Lambda service sitting in the middle and providing things like integrations and intelligent scaling and event source mappings that you are not needing to build and write yourself. So we've talked a bit about scaling, and I think that's one of the things that is particularly unique about Lambda. Obviously, the ability to scale down to 0, but then there's some specific behavior within that scaling that I think is helpful to really visualize. So if you take, for example, a function code, say that last one that we were just speaking about, if there's no requests coming in or no traffic hitting those API endpoints, then nothing is running. So scale to 0, there's nothing that's sitting there always on, idle, waiting for things requests to come in. And so what that means is that when that first request comes in, there is an initialization period. The initialization period includes downloading the code, spinning up the runtime, any of those first steps that are required to get that execution environment up and ready for you to be able to execute the function code. Now, you might have heard this referred to as a cold start period, which you are going to hit every time that you are spinning up or kind of having that first request and spinning up a new execution environment. There are a bunch of improvements that the Lambda service team has made over the years from when Lambda was first launched, as we're on 10 years, as our 10-year anniversary this year. And so those cold start times have reduced across the board for Lambda service. But then we've also been releasing new technology and new features like Snap Start to be able to further reduce those cold start times. So we released Snap Start for Java. Java was the worst offender in a lot of cases for cold start times. And Snap Start for Java allows you to take a snapshot of that execution environment and reuse that. And that led to 10x reductions in cold start time for Java. So definitely worth checking out if you enjoy working in Java. And in the last 2 weeks, we released the Snap Start capability for Python and for .NET. So definitely something to check out if cold starts are something that you're concerned about. After the cold start, any of the following executions are going to be warm starts. So the execution environment is already up and running, and you can just jump in and start executing that code. Now, another interesting thing to think about is what happens when you have an execution in progress and another request comes in. So in this case, this is when Lambda starts to scale up capacity. And then you'll have another execution environment spinning up, another initialization period, and a cold start. And now you have additional capacity, and you're able to process requests in parallel. And Lambda will continue to spin those up as needed for the request volume. Another thing to note about the executions that are coming in is that there is a 5-minute duration or a time limit for those executions. So if the process that you're trying to run is longer than 15 minutes, you can think about is there a way to break that up into smaller chunks and have that be shorter than 15 minutes? Or is this something that might be better suited to run a container and have something a bit longer running? Now, after a while, you might have some requests coming in, executions, but maybe the request volume dies down over time. Now you have some execution environments that are sitting there waiting and aren't having requests that they need to process. And after a while, that execution environment will shut down, and you'll start to scale down, potentially even to 0 if there's no requests. This is another thing to note is that given that the execution environments are ephemeral, you can store a little bit of data in memory or in temp storage, But if you have data that you want to be able to persist longer term, it's very important to externalize that into maybe a DynamoDB database to access that later on. So in summary, Lambda scaling behavior allows you to have very fine-grained scaling and manage auto-scaling based on a per-request basis. So overall, you can see how there's some big differences in the way that containers and serverless functions are built and the type of kind of units of work that they react to. The big kind of difference that I would summarize is the fact that a container is always running. So it's always available, it's waiting there, it might be sitting idle with nothing to process, or it might be processing a lot of requests and units of work, but the container persists regardless of how many units of work there are available. Whereas the serverless function, the entire reason it exists is to process that unit of work. And without a unit of work or request coming in, then the function isn't running. So this is a big difference that you'll see as you're working with containers and serverless functions. Now, one question that this might lead you to think about is, do you need to have a single Lambda function for every single unit of work within your application? And so let's talk a little bit about how we would kind of chunk out the code as part of an application and break that down for Lambda functions. So to provide an example, maybe you have an API endpoint that you're building, and it has various methods. Maybe it has a get method and a get handler to respond to those type of requests, and a post handler. And so you could split those out into two separate Lambda functions and have the code separated in this way. Now, this works great, but you might be wondering, hey, I've got a lot of API endpoints and a lot of methods behind those. So is that going to leave me in a situation when I've got hundreds of functions and a lot of complexity to the amount of functions that I need to deal with? So you do not need to go fully down this route. You can also take a more simplified approach and have a Lambda function backing up each of these API endpoints, and then have the routing to different methods happening within the function code itself. So there's different reasons why you might want to pursue one or the other approaches. Some of the things that you can be thinking about is just kind of standard software design best practices, so keeping code that changes together so that it is part of the same development workflows. Another thing you could be thinking about is, again, thinking about cold starts, is optimizing for those. Maybe your application has a process or a flow where you first create a user and then update the user. Instead of hitting two different cold starts by having two different functions, you could just hit the one and have those two packaged together and optimize for that. You could also think about scaling behavior. Maybe your application gets a ton of GET requests and only a few POST requests. So you could split those out to allow them to scale as needed. You could also think about really finely scoping your permission boundaries and your security. So maybe you have some code that needs to access an order database and some that needs to access an invoice database. And you could split those out into different functions. So there's a number of things that you can think about as you're breaking down that function code and starting to build your serverless functions. And so now that we've taken a quick look at kind of the fundamentals of containers and serverless functions, now we get to the fun part where Max is going to take us through how do we start to make decisions and apply these different technologies for different use cases.
Thank you, Emily. So now after looking into the fundamentals, we now look at different angles, namely operations, integrations, portability, and pricing, and see where are the key strengths in those areas. And the first one we start off with is operations. And in operations we see a broad spectrum. So we see here on the left side we have full control, right? We have full control of the entire stack, of the scaling, of the networking. We can SSH into an instance, we can use a specific AMIs, right? So we are very liberal in what we can do here. We've already talked about how we can reduce some of that with Fargate, right? So we have talked about how the patching and the auto-scaling, for example, is something that we can reduce. And with functions, we can take that even one step further, where even the runtime is managed for us, right? So I can use the Lambda managed runtimes where I have like Java, JavaScript, Python, and even that will be automatically updated for me. Also for placement, I don't need to take care about anything. So the Lambda service will ensure to run my functions in multiple availability zones. So that is not something that I need to think about. Now, when we think about operation, it's not only about control, but also about flexibility and simplicity. And containers offer great flexibility, right? So you have a broad choice of hardware and tools that you can use, right? You can run it on Windows, you can run it on Linux, you can decide what is the specific instance, what should it have, right? How many HDD drives, for example, how large should the HDD drive be? Like how much gigabyte of RAM? Do I want a GPU for machine learning workloads, and so on and so forth. And I also get that deployment flexibility, right? Because of the container runtime, I can run the container in the cloud, I can run it locally, I can run it on-prem. Now, functions, on the other hand, they provide simplicity, right? So we already have the supported runtimes that we talked about, and we can choose a memory configuration, and then the CPU and the network bandwidth will be allocated proportionally. I can decide the processor architecture, so x86 or ARM, right? But the rest will be allocated proportionally based on the memory provided. For local development, I can use frameworks and tools such as AWS SAM to emulate also the function environment locally and have a local developer experience. And now this spectrum from flexibility to simplicity does not only apply in operations, but also in integration. And with containers, and especially the Kubernetes ecosystem, as we have seen before, I'm very flexible here again with the tools that I choose. We have various CNCF-backed projects that you can leverage, things like KEDA or Crossplane, for example, and there's a large community and a lot of documentation and talks around it, and you're very free to choose here. In addition, you're also flexible in the applications that you're running, right? So you can expose any port, so also any form of functionality. So you can export databases, as we discussed before, or message brokers. You can expose an entire Kafka cluster and leverage open source operators to make that operation even simpler, and then build that whole platform around it. With functions, on the other hand, I have a very good integration into the AWS ecosystem. So for example, based on if an object or an image was uploaded to S3, I can trigger my Lambda function, so my piece of code. Or maybe I want to trigger that in a certain step of a step function's workflow. Or I might even want to trigger my function code on a schedule with EventBridge Scheduler and run that every 10 minutes, right? So I have a very good integration. I don't need to write that integration in the code itself, right? I can very easily connect the services here together. And we have seen that before also on the message side. So we have seen that we automatically with the ESM can pull from the SQS queue or read from Kafka or read from a chain stream that we get from a DynamoDB table without needing to write any kind of polling logic. And this can be very, very powerful. Now, besides the great opportunity that lies within integration, sometimes we might ask ourselves, if we have a very good integration, does that come with the trade-off of being maybe less portable? And I want to explore that with you together. And I want to explore that here on two different angles. So I put here the container on the left side and the function on the right side, and we will look at the inbound communication, outbound communication, packaging, as well as orchestration. Now on the container side, as we said, we are very flexible. We can expose the functionality. So that means I can deal with HTTP requests, gRPC, WebSocket, plain TCP port. So I'm very liberal here in that aspect. Outbound communication, the same. I can talk to things in the network, to file systems, to certain databases. And we've already covered the different parts of a container image that makes up that definition, as well as the container orchestration to scale it. So how does that look like on the Lambda side? And Lambda here is actually invoked by the different services, and the structure that I get as an inbound communication is like a JSON payload, and the schema is defined by the service that's actually calling the function. Outbound communication, I can talk to, again, I have VPC-enabled Lambda functions, so I can talk about or talk with things inside my network, and I can talk to DynamoDB, I can also talk to relational databases, and file system also, Amazon EFS, for example, or local temp storage. Now for packaging, you can actually bundle your function code as a zip archive, but also as a container image. We will cover that in a second. And we also need to integrate with the Lambda runtime API to have the link between my actual code and the Lambda service. Now, if we look at this and we want to highlight the most important aspect when it comes to portability, and if we look here on the container side, we see that we need to take some consideration on the orchestration. The container itself, right, has all of its dependencies and is easily portable, but that does not apply to the container orchestrator, right? The orchestrator relies on load balancers, on CNIs, on certain storage drivers, right? And while it might be easy to port your container, porting the whole orchestrator is a bit more involved and requires additional attention when you think about portability. On the function side, I want to first start off with packaging. So you can package your function code in a zip archive and handle it over to a Lambda managed runtime. But if you're already familiar or coming from the container space, you might be leverage your existing container tooling and package your functions as container images. So you can leverage your existing tooling like an ECR, a container registry, you can leverage the CLI, and you can use the official AWS Lambda base image that then establishes the connection to the Lambda runtime API without you needing to add additional things. So you see here a simple example with Python where we just copy in the requirements, we install that, copy our function code, and the only thing that is specific then is we need to provide the entry point so that the Lambda service knows where to invoke my actual function. You can also use your own custom images. So if you have in your company, you have a certain policy and you want to bring your own image, you can do that, but then you need to ensure with the runtime interface client, which is a library that we provide, to establish that communication to the Lambda runtime API so that both parts can communicate. Now, if we go back then, we see that the Lambda runtime API, if I stick to the base images or use the zip bundling or deploy to managed runtimes, usually the Lambda runtime API is not something that I need to deal with. But the last aspect that I want to dive into with you is here the JSON payload, right? So you're not getting here a plain HTTP request to your Lambda function. So if API Gateway, for example, invokes your function, you get that specific JSON payload. And this is different here from the left side than getting a plain HTTP request. So you might ask yourself, right, can we make that or can we get that compatible? And there are frameworks and adapters actually that can help you do that. So we have here two projects, the AWS Lambda Web Adapter or the serverless Java container for Java that actually do that translation for you. So you add that to your function as a library, and what it does is it takes that JSON payload and converts it to something that your framework that you're already using understands. So if you're used to HTTP path-based routing, so things like in Spring Boot or Express.js, for example, you can keep using that because the adapter will take care that your internal framework will understand it. And this might be especially helpful for certain HTTP-based applications, but there also is an alternative that does not require additional tooling and is solely based on abstractions in code. And if you allow me, I would want to write a simple function with you now together in Java. If you're familiar with another programming language, that's fine. I abstracted the code to make it very easy readable. So let's say we want to write a simple function and we want to take an HTTP request from API Gateway and we want to write the headers to a DynamoDB table. So we define here the DynamoDB client and then we write our functions as we have seen before. So we have the handle requests, and as an input we get the API Gateway request, and as an output we return the API Gateway response. So we will define the response here to populate it later, and then we apply some complex business logic here on our headers that we get from API Gateway. We will then create an item, like an ID with a partition key then for DynamoDB, and a value, which is the result of our previous computation. And then we take the DynamoDB client and we just write that into our DynamoDB table. Since we are good citizens, we then also handle error cases. So in case of an error, an exception, we log the error and then we return the API Gateway response, even if it's successful, with a certain status code. Now the question is, do you think this code is easily portable? Yeah, no one, I have guessed that. So you cannot easily take that and maybe replace the API gateway, right, with an application load balancer. If you want to replace the DynamoDB with an RDS instance, right, basically every line here in that code has a dependency to a specific implementation. And now I want to take you on a journey to write that same function again, but with a slightly different approach. And this time, instead of having the direct implementation here, we have an interface, a data repository. And the factory then decides what is the actual implementation that I choose. So for example, I can write a DynamoDB adapter where all the DynamoDB specifics are in there, and I can switch that at a later point if I want to. My core business logic does not rely directly on the API gateway request anymore, but I define my own input or my request object here. And all the things that then are related to API gateway are separate in an API gateway adapter. And this adapter then just calls my transformed headers function. And you see that now all the yellow parts, essentially all the things that are directly tied to an implementation, are abstracted. And if I have that abstraction, what can I do is I can just change that at a later point. So instead of having my API gateway adapter, I might have a traditional HTTP adapter, but the core of my business logic always stays the same. And by having this flexibility, we have seen customers actually leveraging the very same code, but on different compute platforms. So this is a scenario where we want to process items. So that can be order items or a list of complex calculations. And maybe some of those calculations take a longer time. They take more than 15 minutes, more than something that Lambda can handle, right? And in that case, I route it to a queue, which will be handled by my container fleet. But I might get a lot of small calculations, but a lot of them. And therefore, I want to use the scaling characteristics of Lambda to be able to deal with that use case. We can use here a routing layer, such as Amazon EventBridge, to decide based on what characteristics of the message to which of those two I want to route that. Okay? And when we do this observation, so we have the very same business logic, but depending on my scaling mechanisms, or maybe later also pricing requirements, I choose a different compute, we can conclude that the decision when to use containers or functions is mainly driven by non-functional requirements. So you essentially cannot say that, okay, this is a web API, I need to use containers. Or this is that specific application, and this is for functions. You really need to see what are the scaling patterns, the operations, and so on and so forth, and then make that decision. And one of the key factors to make that decision is also pricing. And I want to look at that here first from a container perspective. So container pricing is based on the resource. And resource, I mean either the container or the underlying compute node. And from a granularity perspective, it's built by seconds up to minutes. And to visualize that, we can see here a running container, and we get a few requests. And we define a certain threshold where we want to scale, so let's say 60% utilization. And if we're above that, at some point, a new container will be initialized and will handle that additional load. And if the load decreases, we will then shut down the additional container and just keep our initial container running. If we visualize that by a line, we see here that the actual scaling or also the pricing is not directly tied to utilization, right? So it doesn't matter how many requests I get, right? I always need to pay for the full utilization, of course, right? And this can be especially efficient when I have a very good utilization. So in high load scenarios or constant and predictable loads, right? The more knowledge I have over the utilization, right? The less is the price for my actual single request, the price for the single requests. And if I have the knowledge about the load or the utilization, I can also make certain commitments to it. So for example, if I know that I'm running a database or a very long running workload that has a certain amount of utilization, I can commit to that utilization, for example, for a year or free, and leverage things such as reserved instances or savings plans to make that even more cost effective. Now also factor in the operational cost, right? So we've seen a bit from the operation perspective that you might have an own dedicated team that needs to take care about that, right? So those are also cost factors that you need to think about. When looking at Lambda, however, we see that in contrast to resource-based pricing, the pricing for Lambda functions is based on usage with even a millisecond granularity. So it's very fine granular and automatically scales on demand. And if there's no demand at all, it scales down to 0, which is also very effective when you think about experimenting globally, because you have a very low infrastructure overhead. So if you deploy your functions to US, to Singapore, to Frankfurt, if no one is using them, right, you're also not incurring any charges. And this can be very efficient in an experimentation phase, in a fast time to market and testing out strategies. This can be very, very efficient. So if we combine the two, we see here also where the unique and the core strengths lie, right? So we have here the containers for high, predictable and constant load, and functions for varying or spiky workloads. And we would recommend to make a data-driven decision. So if you don't know your load patterns yet, maybe start with the more flexible approach, and later if you have the data and you know your utilization, then maybe make an informed decision and switch to containers. Or if you know exactly your utilization and you have varying demand on containers, maybe functions make sense, right? So get the data first and then decide which compute platform makes the more sense. And we know this pattern even from real life, right? When we think about having an own car or a car sharing, right? Because with a car sharing app, I can rent as many cars as I like, right? Or as we like, so to say. And if I use them a couple of times, like an hour or a week, right? Or at certain points of a day, this can be very efficient. And I don't need to take care if the car breaks down, right? Someone else will do it for me. However, if I use a car sharing app for 24/7 for the entire week or the entire month, that can potentially get quite expensive because I also don't need all that flexibility, right? And in that case, having your own car and having that predictability might be a more efficient model. And now that we have understood the basic categories to make that decision, we will now apply them and look into real-world customer examples and see how that decisions have been made for customers.
All right, so I am going to wrap us up with 4 customer examples of customers that we've worked with that are building really cool modern applications. And the cool thing about these customers is that they've all made different decisions based on what was going on for them. So some customers have chosen to go fully containers route, full platform engineering approach. Some customers have entirely leaned into Lambda functions and serverless for their event-driven and spiky workloads. And then interestingly, a few customers have combined the two. So maybe they have an application where there's pieces of it that make a lot of sense for containers or are well suited for serverless functions. Or maybe it depends on where they're at in their modernization journey. So continuing to evolve their application to advance it and to set it up for success for what their business needs might be in the future. So let's jump into some of those customer stories. The first one that I have for you is Delivery Hero. So Delivery Hero is based out of Berlin and operates one of the world's largest food delivery networks. And Delivery Hero has a number of different subsidiaries. And what they were finding is that across all of their subsidiaries, they all had similar requirements when it came to the infrastructure that they needed to run their applications on and the tooling that they were looking for to be able to do that. And so Delivery Hero took the approach of building a container platform that would provide that standardization to really standardize the way that all of the developers across the subsidiaries were creating and deploying and operating their applications. So Delivery Hero chose to build with Kubernetes and build out with EKS. They have over 300 EKS clusters and 15,000 compute nodes as part of the platform that they build that serves 10 million daily orders. They're using a number of tools from the Kubernetes ecosystem, things like Istio, Argo CD, and Carpenter. And they're also deploying AWS services in a Kubernetes native way using the AWS controllers for Kubernetes or the ACK tool set to be able to deploy those. This is a great example of a customer that took a platform engineering approach and built out a very robust platform to standardize across a very large number of developers. In total, they have about over 200 platform engineers that are working on this platform and also providing abstractions and blueprints to the over 3,000 developers that are building and deploying their applications on top of it. Next up is the UK Driver and Vehicle Licensing Agency. So DVLA is part of the UK government that maintains a national register of drivers and vehicles for the UK. Now recently they embarked on a very large-scale modernization of their driver services applications. So this included a full update and an improvement of the front end and the presentation layer, but also a really substantial modernization and refactor of the back end to make the best use of cloud and set themselves up for success and keep evolving their application going forward. Now, the interesting thing is that they've taken both approaches where it makes the most sense within their architecture. So first off, they have a containers platform, again using Kubernetes and EKS. And what they've done here is they've built very standard components for some of the type of applications that they need to run. So they have a standard component for the way that they run UIs with Ruby on Rails. And they also have a standard component for Java. So they have a very stable and mature Java stack that they run as a container. And that allows them to use over 100 Java components and libraries, make use of Java best practices like connection pooling for accessing their databases. And there's over 100 developers that are making use of this containers platform to build their application self-service. But then when it came to the application, so driver's license application processing backend that they needed to build, they realized that this workload could actually be really well suited for serverless, given that it was very event-driven and really optimized for doing asynchronous processing. So just to give you an idea of how kind of the flow of this application would be from end to end, say that you are coming onto the website looking to submit a new driver's license application. You navigate through the UI, make some requests on the front end, and then your request and that information that's going into your driver's license application would hit the back end. Now there's obviously lots of details about you that you're applying with, but another important piece of it is the photo that you want to go on your driver's license. And so they have some checks that they need to do in terms of is it the right size, any post-processing, but importantly they want to make sure that it's a valid photo because it is going on an important document. So they want to make sure that it's clear, it's not a photo of your cat, any of those kind of checks that they might want to do just before that goes on the official document. Now, this process, they have a step functions workflow using Lambda functions that steps through those checks. They are using AI/ML to support the process, so services like recognition to do some initial checks of what that image contains. But it does need to be a human that makes the final approval. So there's a human in the loop in this workflow. And this is particularly well suited for asynchronous processing because the human could be sitting at the desk or ready to submit it, to hit that approval in a few moments. Or it could be, the form could have been submitted on the weekend and it could take a few days before someone is able to make that approval step. And so the step functions workflow uses a wait for callback token step, pauses the workflow, there's nothing running idle waiting for that human to submit approve, and then when the callback token comes back, the workflow kicks off again and the serverless components are running and continuing processing. So a very cool example of a customer that's built a very modern new application and has taken the best of the containers platform and serverless for different use cases within that. Next customer that I want to speak about is Autodesk. So Autodesk was building a new product, Autodesk Forma, that would allow architects and designers to be able to run simulations to understand the environment and climate and how that would interact with the designs that they're building. And they wanted to be able to build very iteratively and to get those simulations running and those insights back in near real time. Now, they initially were working with Kubernetes to try this out and started to build out with Kubernetes. But what they found is a couple of characteristics of the workload. First off, these simulations were very resource intensive and they're very kind of variable demand. So as an architect is working on something, you're not really able to predict when they're going to need that simulation. And so the demand was quite variable. And they found that Kubernetes was challenged to scale up as fast as it needed to. And the additional steps of just the operating and maintaining their Kubernetes clusters were some additional overhead that they weren't interested in doing. So they instead opted for a serverless and a Lambda function-based approach. And this is the workflow that they've got to run those simulations, where you have Lambda functions that are triggering a new analysis, preparing the input, and taking that job and chunking it out so that it can run with many, many parallel Lambda functions, and then collecting and combining the results. And all of this is able to scale up very quickly and to process very quickly with the amount of parallelization. Another cool thing about this one is that they had some simulations that required GPUs. So some simulations needed to do ray tracing of sunlight irradiance on buildings. And because Lambda doesn't support GPUs, but ECS does, and so they were able to just switch out when they needed a simulation that needed GPUs to instead run that with ECS. And the last customer example that I will talk through is Lexware Office. So Lexware is a company out of Germany that provides a SaaS accounting product. And what they were doing is they initially had this SaaS product running on-prem. And they found that this was they were running into bottlenecks and performance issues. And so they decided to instead move this over to the cloud. They initially did just a kind of lift and shift of the application as it was, but even that just enabled them to be able to reduce the bottlenecks and performance issues and onboard 90,000 new users to their application. But then they took a look and said, hey, I think we can continue to modernize from here. And so they took part of their application and containerized it, and also looked for parts of their application that were event-driven and spiky in nature to start making use of serverless functions. So the example use case that they have here where they've started to use serverless functions is when they want to send event notifications of when an invoice is paid in the SaaS product, and send that on to a user-configured HTTP endpoint, so maybe an external system like a CRM or an ERP system that needs to be updated when an invoice is processed in Lexware Office. Now, the reason they thought this was going to be a great fit for serverless is just because of the load patterns, which you can see down below here. So because invoices are typically paid maybe one time a month or on a particular schedule, this was a very spiky workload. So it would spike up to 8,000 requests per minute, and then it would drop down to nothing. And so it didn't make sense to have kind of always running capacity on to be able to handle that. So how the system works is when a new event is generated or a new message is put on the queue for a new invoice being paid, there is a very small Lambda function, so just 128 megabytes in node, and it's a webhook function that retrieves a message and looks up in a DynamoDB table what the user-configured HTTP endpoint is that event should be sent on to, and then it makes that call. And those very small Lambda functions are able to scale up and then scale back down in an event-driven way. So this is a cool example of how we see customers that are taking their application and refactoring it and modernizing it, maybe using a bit of containers, a bit of serverless functions, and continuing to kind of take that application and modernize it for future use cases. All right, so I will go ahead and wrap us up with just a few of the key takeaways and summarize things that I hope you learned from Max and I's talk today. So thinking about the key differences between containers and serverless functions. The first characteristic to think about is the lifecycle and load profile. So containers are instantiated, they're always running and can handle multiple units of work until terminated. This is a great fit for your more constant or predictable workloads that have a very steady volume of usage. Whereas Lambda functions are beginning with invocations, they're only running when there's a request there to process, scale up tremendously and scale down to zero, which is fantastic for spiky and variable use cases. The next piece is operations. So with containers, you get a much higher degree of control and flexibility and configuration options. But with that, you also take on a fair amount of responsibility. You can offload some of that as you look at options like serverless containers, but this is definitely something to think about that you're taking on to manage yourself. Whereas on the serverless function side of things, you take advantage of much more fully managed and highly available experience with AWS handling a lot more of the operations for you. On the integration side of things, with containers, you have a choice of the broad open source ecosystem that's available to you and things that you can use there. Whereas with functions, you get a lot of optimization of just out-of-box integrations that come to connect your Lambda functions to other AWS services. Things like those event source mappings for the upstream event sources that we talked about are baked into Lambda and code that you don't need to write yourself. Portability. So with containers, obviously this is very simple on the application layer for you to be able to just take the code that you're running and have that in the cloud, on-prem, wherever you might need to have it. But of course, there's pieces of the infrastructure layer that you might need to change if you were going to pick that up and move it somewhere else. On the function side of things, you can definitely take advantage of things like deploying your Lambda functions with container images, frameworks, and hexagonal architectures to be able to abstract the implementation details and just have that business logic, and then make your function code a lot more portable should you need to evolve that over time. And lastly, pricing. So with containers, because those are always on, you get kind of resource or compute node-based pricing, and it's a bit more coarse-grained. Whereas with functions, the pricing is very tightly tied to usage and is very fine-grained to changes as your request volume changes. So if you enjoyed this session, I hope you got a lot out of it, and there's a few other sessions that you might be interested in. You can catch me actually later today at the Kubernetes and serverless, bringing together the best of both worlds and deploying serverless EDAs with Kubernetes later today. And then we also have some great sessions on modeling costs for serverless applications and celebrating 10 years of Lambda and ECS in our leadership session. So thank you so much. Please do give us some feedback. And for Max and I, thank you for joining us.